Look at a jagged mountain range or the path of a rushing river. The natural world is chaotic, weathered, and highly unpredictable. But occasionally, the Earth spits out something that looks completely engineered. Take halite, commonly known as rock salt. It forms precise, flat-faced cubes with exact 90-degree corners, rhombohedra, structures that look like cubes pushed slightly off-center, resulting in slanted, interlocking planes. Nature doesn't use microscopic rulers or milling machines, yet deep underground, it autonomously builds flawless, straight-edged architecture. This physical precision indicates that a highly organized, strict set of rules governs matter long before it reaches a size we can see. To figure out exactly what those rules are, scientists rely on crystallography. It is the dedicated study of how atoms are arranged inside solid matter. Looking at the exterior shape of a mineral only provides a fraction of the data. To map the true physical properties of these materials, we have to drill past the visible surface and observe their atomic foundation. If you shrink down to the scale of atoms, you find that the particles in a crystal do not sit randomly. They lock together into a rigid, repeating three-dimensional grid. You can think of this structure like a wall built out of identical Lego bricks, or a floor covered in identical tiles. The single, smallest repeating block of that structural pattern is called the unit cell. As a crystal grows, it simply copies that exact blueprint over and over, stacking millions of unit cells in every direction. A heavy, visible crystal is really just one microscopic geometry equation scaled up billions of times. The micro dictates the macro. But if all crystals are built from repeating blocks, why does salt grow as a cube while quartz forms a hexagon? The answer lies in the specific lengths and angles of the internal connections. The laws of the universe restrict crystal growth into exactly 7 distinct architectural styles, the 7 crystal systems. Atoms bonding at equal lengths and 90-degree angles generate a cube. Shift that connection slightly, and the entire lattice tilts, generating calcite's slanted rhombohedral structure. The overall shape of a mineral is entirely locked in by whichever of those 7 structural systems its atomic bonds dictate. This strict internal organization also produces a crystal's symmetry. In crystallography, symmetry isn't an aesthetic trait. It is a rigid, measurable physical property. Think of a perfectly formed snowflake. If you spin it around its center, it snaps into a position where it looks completely unchanged at specific, equal intervals. This visual consistency demonstrates its rotation axes and mirror planes. What you see from the outside is a direct reflection of how perfectly balanced the atoms are on the inside. Because almost all solid matter has an atomic structure, these same laws govern the materials we interact with every day. Material scientists map out unit cells to determine the structural limits of industrial metals. They use these exact principles of repeating geometric lattices to manufacture the highly precise silicon wafers that run semiconductor technologies. Biologists rely on crystallography as well. By bouncing X-rays through crystallized organic matter, they map the intricate structures of proteins, develop targeted medicines, and decode the complex double helix of human DNA. Mapping atomic patterns provides the universal toolset required to manipulate the specific materials that keep the modern world running. A crystal is nature's mathematical rules rendered in solid form. Every piece of matter carries an invisible atomic blueprint. Crystallography is the science that allows humanity to read it, decoding the chaos of the natural world into organized order.